All right, the purpose of this video is to walk through the Hubble Lemaitre Law Lab. So let's start by looking at the module. All right, here we are in the template file, and you'll see the purpose of this lab is to determine the current numeric value of Hubble's constant and the age of the universe using real astronomical data. This lab will require teamwork among your peers to accomplish. This lab also requires 2 weeks to finish, and this is the first week. Here are the things we're going to need. We're going to need the template file, which is the file that we're looking at right now. We're going to need Excel. We're going to need the Table 1 PDF file, which is a list of data pages that are assigned to students. We're going to need the findings discussion, which is where we share our findings, and then the questions. All right, in the background information, there's a lot of useful information about cosmology and how the expansion of the universe was discovered by Edwin Hubble. This is him. And Georges Lemaitre. This is him on the left-hand side. Both of them sort of independently discovered it. Lemaitre did it theoretically, whereas Hubble did the experimental work to show that Lemaitre's prediction was correct. For years, this law was known as Hubble's law, but has recently, within, say, the last 10 or 15 years, been renamed the Hubble-Lemaitre law. All right, and this little equation that you see right here, this is actually Hubble's law. It says that velocity, and this is going to be radial velocity, this is the recessional velocity with which a galaxy is moving away, that's v, is equal to a constant called h naught. That h naught is known as Hubble's constant. Multiplied by d, and d is the distance. So how fast a galaxy is moving away is directly proportional to how far away the galaxy is. That's what Hubble's law says, and you can make numeric calculations using this equation here. If you were to plot redshift, which is related to velocity, this is proportional to velocity, so you can almost think of this vertical axis as being velocity, radial velocity, versus distance in megaparsecs. You'll see these blue dots represent experimental values for redshift and distance that are plotted together. And you can see this red line is a linear fit to that data. And you can see that it's a pretty good fit to the data, which is where Hubble's law comes from. Now we're going to use NASA's IPAC Extragalactic Database, what I'll call the NED. That is the NASA Extragalactic Database. That's what NED stands for. And the NED is operated by the Jet Propulsion Laboratory at Caltech, which is under a NASA contract. And this database contains real astronomical data. And we're going to query the database, we're going to get real data, and then we're going to analyze it. And like I said, this requires teamwork. It's pretty much independent the first week, and the teamwork will come in the second week. All right, and then here's the procedure, and you can see the procedure is divided up into parts. The first part is determining redshift and radial velocity for a specific galaxy. Then part 2 is retrieving the radial velocity and distance for a group of galaxies, which we will use to create our own Hubble plot. And then we need to format the return data. And then in part 4, we plot the data. We create our own graph. Yours may look like this, but odds are it won't look exactly like this at all. And then in part 5, we will use our graph to determine the Hubble constant, the value of h naught, and we can also use it to determine an approximate age of the universe. And we will submit our findings by sharing them with the class through the discussion, and you will also upload your completed Excel file through the questions. Okay, and that's that. You'll notice there are no follow-up questions at the end. The follow-up questions will be in next week's lab. All right, so let's scroll back up to the beginning of the procedure and walk through this. Okay, it says for this first part, you will come to appreciate how radial velocities are computed for actual spectroscopic data. First thing we need to do is we need to go to the NED database, and here is the link that is provided. Let's click on that link and get started. All right, when you click on the link, this is what appears. And we are interested in this data column. Specifically, we are interested in the spectra, and we are going to query a galaxy known as NGC 1050 and find its visual spectrum. So let's do that. Click on the spectral link right here. And now we need to enter in NGC 1050. And if you care, there is a link to an image of that galaxy in the template. All right, next step is we need to find the spectra. So there are lots of tabs here, lots of information about this galaxy. Let's click on the Spectra tab. And it brings up several spectra. Looks like there's 4 different spectra here. On the right-hand side, it tells what the coverage of the spectrum is. This is an optical spectrum. This is an optical spectrum. This is a hydrogen 1 or H1 spectrum, another H1 spectrum. So the one we're interested in is this one right here because it covers most of the visual optical spectrum. It starts at 5,445.3 angstroms and goes to 7,899.6 angstroms. And if you remember, the optical spectrum goes from 400 nanometers to 700 nanometers, and that turns out to be 4,000 angstroms to 7,000 angstroms. All right, so we want this spectrum right here. The way you download it is through these links over here on the left-hand side. The one we're interested in is the ASCII one, which is just text. Now, if I click on Author ASCII here, you'll notice it gives me a whole bunch of data. This is the data that we want, but we need to download a file with this data in it because it just goes on and on and on. You'll see on the left-hand column, this is the wavelength, and you can see it starts at 5,445, and then what's on the right-hand side is the flux. You can think of this as the intensity of the light coming from the galaxy at the specific wavelength that's on the left. All right, so let's go back here. And instead of clicking on Author ASCII, let's right-click and do a Save Link As. This will save it to a file. That file is saved to my Downloads directory. I can move it to a safe place now if I want to. But what I really want to do is I want to import that file into Excel. Let me show you how to do that. Let's begin by opening Excel. Now, when I first bring up Excel, I want to open a blank workbook, so I'll click on that. And now I want to import my data, so I'll come up here to File, Open, and then I will browse to that text file that we just downloaded. Now you may notice whenever I go to that location, I cannot see the file. That's because it is only looking for Excel files at the moment. So come down here in the bottom right-hand side and choose All Files. And now I can see the text file that we just downloaded. I'm going to click on that and open. And what it does is it brings up a text import wizard. You can see a preview of the data down here at the bottom. If I were to just open the file right now and say finished with this text import wizard, it would put all of that data into one column in the Excel file, which would be useless to us. We don't want that. What we want to do is we want to divide the data so that the wavelength is in one column and the flux is in another column. So we're going to choose delimited data, and then we're going to hit next. Now the data is delimited not by tabs but by spaces. If you hit space, you can leave tab checked, but if you check space, notice what it did down here in the preview window is it divided the wavelength and the flux. It also has some extra columns out here to the right hand side, but I don't really care about those. So I hit next and then I hit finish. Now it says, do I want to convert this? What it's going to do is it's going to convert everything that has an E in it to scientific notation. And yeah, I do want that. So when I hit convert, so here now is my Excel file, and all of the data has been converted into numeric data. And anything that has an E in it is treated like scientific notation now. One of the first things I need to do is get rid of this second row here. I don't really need these units, so I'm going to get over here on the left-hand side till my cursor turns into an arrow, and then left-click and I select the whole row. Then I get anywhere on the row and I right-click and I choose delete, and I got rid of that row. Now I need to spread these columns out a little bit, so I'm going to select both columns and then move over so that my cursor changes. You can see when my cursor changes to that, then I can double click and it will space out the rows to be perfectly aligned. Okay, there's a lot of data here. If I scroll down to the bottom, it looks like there is 800 data points here, and I want to plot all of this so that I can see where the hydrogen alpha line is. Hydrogen alpha exists as a prominent spike in the NGC 1050 spectrum, and I want to find out where that spike is. What is the wavelength at which that spike occurs? You'll see the spike when I do this. Let's select the two columns and now do Insert, Chart, Graph, and I want to create a scatter plot. But I want to do a scatter plot that is just lines. If I put data points on there, there's so many of them that it really gets lost. So let's just do the lines. So scatter with smooth lines. And this is what we get. Now we need to fix some things here. We need to name the axes, but you can see there's a very prominent spike here in the data, and that's what we're after. So first thing I'm going to do is I'm going to resize the graph so the data is actually more prominent. You notice it starts here at 0 for the wavelength, but our data didn't begin until, what, 5400? Let's change this. I click once to select this axis, and then right-click and choose Format Axis. This pops up, and the bounds, the minimum, I want to change that to 5400. And let's set the maximum to 8000. And there we have a nice looking graph. Let's make it look pretty. And this is NGC 1050 spectra. All right, we need to label also these axes, so I'm going to select the graph once. Be sure I've got the Chart Design tab selected, and then come over here to Add Axis Titles. We'll choose the primary horizontal and then go back and also choose the primary vertical. And now I can label these. Now, here's the point. I want to find where is that peak at. Specifically, what is the wavelength down here on the horizontal axis where that peak occurs. Now, there's a couple of ways you can do this. The easiest one is to move your arrow right there to the top, and whenever I do that, it's telling me that there is a point right there. Remember, I did not put markers where the points are, but it's telling me there's a point there that has a wavelength of 6654.03 and a flux of 2.47 times 10 to the negative 14th. So that's the highest point here, 2.47 times 10 to the negative 14th. That corresponds to the high point. And the wavelength is 6654.03. So I'm going to write that down, 6654.03. Now, if I go back and I look at the template at this point, my plot does look like that. I have made mine prettier than the one that's in the template, though. There are 3 questions that I need to answer. You notice it says Q10A.1, here is Q10A.2, and then here's Q10A.3. I need to jot those down, or to be honest, I think the easiest thing to do is to keep track of them inside of the Excel spreadsheet. So I'm going to do that. You will need to read these instructions about what you need to do here. But I'm going to go back to the Excel spreadsheet, and I'm going to use the H alpha observed. That's the spike of the hydrogen alpha line that we just observed. That one was the 6654.03 angstroms. So I'm going to write that down inside my Excel spreadsheet. So let's go back to that. All right, so back here in the Excel spreadsheet, that was Q10A.1. And there's also a Q10A.2 and a Q10A.3. Now, I'm just putting those there. I'm going to put the numeric values over here to the right of that. That first one was 6654.03, and that is angstroms. And then 10A.2, if you'll go back to the template, I'm not going to go there, but it says you need to calculate the Z value. Now, the Z value is related to how much redshift is present here. The hydrogen alpha line is at 6,562.8 angstroms. You can read this in the template. So 6,562.8 angstroms is where the hydrogen alpha line is in the laboratory when there's no relative motion between the observer and the source. However, in this galaxy, there is a redshift, and I've just said the redshift is 6,654.03. So the difference between that and the hydrogen alpha line in the laboratory, that amount right there is going to help me determine what the Z value is, or the redshift value. So here's the way this works. I'm going to use an equation, a formula, and I'm going to say equals the observed value, which is what we have up here, minus 6,562.8 angstroms. So I am going to click off of that. When I do, you can see it created a number here. When I click back on it, I can go up here to the formula line, to the formula bar, and I can put parentheses around that. And now divide by the 6562.8 one more time. And there is my Z value. And there's no units attached to that. That is actually the percentage of light speed that this galaxy is receding away. And you can see it's like 1.4% the speed of light. Okay, the next thing, once again, look in the template for this, for the instructions. We need to calculate the radial velocity. And the way that we do that is we multiply the Z value by 299,793. So let's do that. Equals 299,793 times the Z value. And that is in units of kilometers per second. So km/s. There we go. Now I will need these values later on, so I'm just putting them here so I can recall them. Okay, now what we have just done is we have determined how fast NGC 1050 is receding away from us. It appears to be receding away from us at a speed of 4,167.446 kilometers per second. And we did all of that by determining what the redshift was. Now, if we were real astronomers and our job was to determine what the Hubble constant is based upon some of the data in this galaxy database, then we would have to do what we just did for all of the galaxies. However, I know that's a time-consuming project, and we would do it for 100 or 1,000 galaxies. We don't want to do that. But fortunately, it's been done for us already by a lot of other astronomers. So here's what I'm going to do. I'm going to create a new sheet, and I'm going to go down here to the bottom, and you see the plus sign here. It says new sheet. It creates a new spreadsheet here. So I'm going to click that, and it created this. It calls it sheet 1. You can rename that if you want to by right-clicking and choose rename. It doesn't matter what you call it. All right, part 2 of the template is where we retrieve the radial velocity and distance data out of the NED database. And there's a lot of data here, so let's go through the process. First of all, it tells us to go back to the database again, and we can click on that link right there to do that. And we're going to look up some objects, and we're going to query the database. Now, all of the information that's here is necessary for you to understand what specific boxes need to be checked on the NED website in order for you to get the data that we want. So my recommendation is to read this section carefully and make sure that you've got all of the right boxes checked and not any extras. So I'm going to click here on the link, and I'm going to open up the NED website one more time. Okay, here we are at the NED website one more time, and this time we're interested in the objects column over here. We are going to search for objects by classification, type, and attribute. Let's click on that. And whenever I do that, it brings up this user customized output table and index of constraint types. By checking these boxes, we are constraining our search to whatever the box chooses here. Now at this point, none of the boxes are checked, so it's not going to return anything at this point if we were to submit our query. We need to find specific galaxies that we're interested in. And for our exercise, we are only interested in spiral galaxies. So let's do this. Click that checkbox right there for spirals. And that's it. Now, we don't want it to return extra data. There's only specific data that we're interested in, so we need to tell it which data to return. The way we do that is we go up here to the top to User Customize Output Table Columns, and we click on the Show/Hide Customization options. When I click on that, it brings this up, and you'll notice that there are separate blocks here, and there are a lot of blocks. The constraints are also included down here at the bottom, but we don't care about the constraints anymore. We're only interested in what data needs to be returned. Now, for each of these blocks, there are already boxes that are checked, so there are default values here. What we need to do is we need to uncheck several of the boxes and then only check what we want. So here's what I always recommend you do. Go through and uncheck absolutely every single box. Look in this block and then look in this block, make sure there's nothing checked. Look in this block, make sure there's nothing checked. Uncheck if there is. Now, for this specific block that we're looking at here, there are some things over here to the right-hand side. So scroll to the right and uncheck those boxes as well. And I think that's it. So the detailed information block, everything has been unchecked. The extinction block, everything has been unchecked. And the general table features, everything has been unchecked. Okay, now that everything is unchecked, let's go through and make sure that we check only the things that we want. So first of all, delimiter. We want the tab to be our delimiter here. And we do not want hyperlink. So check that box to turn off hyperlink. Under standard information here, what we want is the row number, the row count, and we want the NED's preferred object name. So these top two things in that column. And then over here under basic data, we want the radial velocity. So check that one. And then that's it for this top block. Let's scroll down. There's nothing in this second block that we need, but under detailed information down here, there are some things that we need to check. And the things that we need to check are over here on the far right-hand side. What we need is metric distance in megaparsecs. Now notice over here, after we check the metric distance in megaparsecs, there's a note here that's going to be important to us later on. It says these summary statistics are provided for quick look reference only. They are based exclusively on original values as published. No homogenization or corrections have been applied. That means that some of this data, especially for distance, may be bad data. They're giving us a warning here that there's been no corrections or calibrations of the data. So we need to be aware of that when we're creating our data plots, because some of the data may be spurious. And you'll see that, I think, whenever I create the plot for you to see. That also means that we may need to exclude some of the data just because it's bad. And you'll see what bad looks like, I think, in just a moment. And that's it. And we're ready to submit our query now. Now you can hit any of these submit query buttons. Any of them will work. All right, this is what NED returned for us. And you'll notice the data is in this gray area down here. You'll notice it tells us that the objects have been sorted by right ascension and declination, but keep in mind we are not displaying right ascension and declination. We are displaying this row number here. Here's the object name in this column. Here's the CZ, which is actually the radial velocity. It's C times Z in kilometers per second. Here is the distance in megaparsecs, and we've got row number again on the right-hand side. If you'll look, it says there are 38,060 objects that are found in the NED database that meet our criteria of being spiral galaxies. So that means there's 38,000 spirals in the database. That's nowhere near all of the spirals, but that is still a lot. If you scroll down to the bottom here, you'll see there's only 100 rows of data. But also read down here at the bottom, it says that this is page 1 of 381. If I go to the next page, this is page 2. See, it says page 2 of 381. And I go to the next one, there's page 3 of 381. I can also go to any page I want to by entering that page number in here. So let's say I want to go to page 8. Okay, page 8, hit go, and now this is what's on page 8. And each time it only gives me 100 objects. Now you are not responsible for doing all of these objects. You are only responsible for certain pages. Go look at the table 1 file. Remember that file? Look at the table 1 file, look at your name, find your name in there, and the table will tell you what page you need to start on and what page you need to end on. Everybody has the same number of pages. So what I'm going to do is I'm going to go to page 1 and I'm going to do what you need to do, but you need to do it on your pages. All right, so here's what needs to happen. We need to take this data and we need to put it into a text file, and then that text file we can import into Excel and do our analysis. The easiest way to do that, in my opinion, is to come over here and literally select the data. So go all the way down to row 100. Be sure you don't go past that and select extra stuff, but select that last 100 there. Now that I have that, I can do a number of things. I can right click and I can hit copy, or I can do Control C on my keyboard. Control C copies whatever has been highlighted. So now that I have all of that highlighted, I'm going to open up a text file and I'm going to use WordPad. When I open up WordPad, it looks like this. What I can do is I click once in here and then I can right click and paste. And there, it just pasted all of that data. You'll notice it's kind of ugly, but that's okay. Remember, there are tabs in between these data columns because that's the delimiter that we wanted. Now, after I paste my first page on there, you notice my cursor is right behind 100 there. Be sure you do this. Be sure you hit enter, and now you're ready to start your next page being pasted here. Remember, you only have to do a limited number of pages. You're not responsible for every single one of the over 350 pages. So I'll go back to the NED and I'll go to the next page. And this is page 2 because I started on page 1. And I'm going to select everything here. Be sure you get the last 200. And now Control C, go back again to my WordPad, and Control V. There, it copied the next 100. I'm going to continue to do this for, let's say, 6 pages. So I've done 2 so far. All right, so I've done 6 pages of data here. Remember, you should do the pages that have been assigned to you in the Table 1 PDF file. And now that I have that, I need to save, and I need to save it specifically in text format. So I come up here to File, Save As, and I choose Plain Text Document. And I'll save it to a spot that I remember and I can get to easily. So I'll put it on my desktop, and it doesn't matter what you call this, so I'm just going to call it document.txt. It's warning me that I'm about to save the document in a text-only format, but that is exactly what I want to do, so stop questioning me about that. So yes. Now that I've done that, I can close my text file. I'm finished with the NED database, so I can get out of that, and I need to go back to my Excel file. Okay, here I am back in the Excel file, and you'll notice that I'm on the second sheet, the one that I created here. And what I need to do is I need to go import that text file that we just created. So I'm going to go up to File, Open, and I'm going to browse to that file. Once again, the text import wizard pops up, and we have delimited data, so we'll click that and hit Next. And it looks like it divides it up very nicely because the tab delimiter has already been selected. So I'll click Next and then Finish. And with that, Excel opened up a new document. But that's okay. What I like to do is I like to select all of this data. I'll come over here, select the entire columns, hit Control C to copy the data, and then come over here to the other file, and I will paste the data. And now I have all of my data, including that first sheet. Remember that first sheet was back here. I am now on sheet 1, and this is the data that I'm going to use to create my Hubble plot from. We have a row number in the first column, but we also have a row number in the E column over here. So let's get rid of that. So I'm going to select the E column, the entire column. I'm going to right click and do delete. So we got rid of that. Now we need to add some column titles up here above the data. So I'm going to come over here to the 1. I'm going to left click to select the whole row. And then I'm going to right click and do insert. When I do that, it inserts a new column above what I had selected. And let's label these. This is row number. The second column is galaxy name. The third column is the radial velocity, so we'll call that V radial. And we'll put the units in parentheses, kilometers per second. And then this last column is distance. I'll just call it DIST. And it's in units of megaparsecs, capital MPC. Now some of the column headings are cut off, so let's resize this. I'm going to select all of those columns, get up here at the top until my cursor changes to that, and whenever it does that, I double click, and now it has resized all of the columns to be as wide as whatever the widest thing in that column is. All right, now we're not finished yet. You notice it has a radial velocity, but there's no distance present. For all of these that do not have both radial velocity and distance, we need to call those out. We need to get rid of those. Now the template tells you a method to do that, but I think I have a faster way to do it, so let's do this. So here's the way I do it. Come up here to Data, Sort, and the sort window opens up. Be sure you have this box checked. It says my data has headers, and our data does now have headers. And then I'm going to sort by, and here are all of the header names. First thing I'm going to do is I'm going to sort by radial velocity, so let's click that, and then I hit OK. Now you'll notice what it did is it put everything in order of radial velocity from the smallest value at the top to the largest value at the bottom. But if I scroll all the way down to the bottom here, down here there are blank radial velocities. So I can select all of those by just selecting the individual rows. So I click once on the first row and then I drag down and I select all of those rows. Now I need to get rid of those. Those are galaxies without any data points here. So I'm going to right click and then delete. If I had left those there, it would have made our plot incorrect. All right, now we've done that. Now I'm going to scroll back up to the top. Now we need to do the same thing for distance. So I do Data, Sort, and this time I'm going to have it sort by distance. I hit OK, and once again it has sorted by distance. I'll scroll down to the bottom of the distance, and right here there's no more distances present. So now I'll select all of these because all of these are lacking distance. Okay, so I selected all of those rows because those galaxies are lacking distance. There's a lot of galaxies there without a distance. And I'm going to right click and once again delete. Now I'm going to do one more sort, and I'm going to sort by row number. This is an important step for you. You want to make sure that you do this last part and sort by row number. One of the things that I check when I'm grading is, did the student use the correct data? Did they use the data that was assigned to them specifically? One of the things I look at are these row numbers over here to the left-hand side. So be sure you do that final sort. Okay, one other thing we need to do before we create our plot is we need to reverse these two columns here. But I found the easiest thing to do is just to select this entire column. I hit Control-C to copy it, and then I'll come over here to this blank column, which is to the right of distance, and I will do Control-V, and that copied that entire column over there. And then I'll go back here to the column that I just selected, and now I will right-click and I will choose Delete. Now that was necessary because when we select these two columns to create our plot, the distance will be along the horizontal axis and the radial velocity will be along the vertical axis. And it will just happen naturally because of the order of these two columns now. Now, one of the last things that I want to do is make sure all of the galaxies have both a distance and a radial velocity. So just very quickly, I'm scanning the data and looks like everything has both distance and radial velocity. And I have 147, so 146 data points that I'm going to plot. All right, so now that we're at this point, one of the best things we can do is save our files. So let's be sure and save as. Be sure you save it as an Excel file. So come up here under Excel and let's name it something meaningful like Hubble Lemaitre Law Lab 10A. And then we'll save it to a place where we know. At this stage we are ready to plot our data, so let's select these two columns here. Select the entire columns, come up here to do Insert, Charts, and this one we want to be a scatter plot. So we'll click Scatter. And here we have our scatter plot. And this is what I meant by some of the data may be bad. This point way out over here is all by itself. That is uncalibrated data. So that data point right there should be excluded. Now, if it is excluded, I need to keep track of the fact that it was excluded because when I write my final report, other astronomers may want to know that I excluded one specific data point. So I look at that, I hold my cursor over it, and it says that has a distance of 1,270 and a radial velocity of 13,263. So 1270 is the distance that I need to exclude. Now here's the easiest thing to do to find that. I will just click off of the graph and I will hit Control plus F. That is the find function. So I'm going to find that specific data point. I'm just going to type in 1270 and there it is. So this data point right here, I'm going to exclude. Now, I need to make a note of this. This is WISE AJ0006028.88-004703.5. I would write that galaxy name down and I would include that in my final report as a data point that I excluded because I thought it was spurious data. After I have written down the name of that galaxy, and I select the whole row, right click, and delete. Now let's see how that changed our graph. Oh, that changed our graph pretty well. Now, you might say, well, this data point may be bad as well. Yeah, you could exclude that one if you wanted to. If you do exclude that data point, then be sure and write it down. Write down the galaxy name so that you can report that one as well. But that one looks like it's not too far off of a straight line here, so I'm just going to leave it. Now I do need to do some important things here. I need to change my graph name. I also need to have axis titles here, so I'm going to click on the bottom. Now that we have done that, we're ready to do the science. If you recall from the template that V equals h naught times d is Hubble's law, or the Hubble-Lemaitre law. H naught is called the Hubble constant. The point here is that if I plot V on the vertical axis and I plot d, distance, on the horizontal axis, then the slope of the line should be Hubble's constant, and that's what this shows down here. All right, let's go back then and put in our trend line and determine what the slope is. So back here in Excel, we have our data plotted. If I click once on any data point and then right click, I can click now Add Trend Line. This is going to be a linear trend line. I am going to set the intercept to be 0 because 0 distance means 0 radial velocity. I want to display the equations so that I can read off what the slope is. And then I want to display the r squared. Remember, r squared is the goodness of fit parameter. If it is close to 1, then we have a really good fit. Now that I've done that, I'll close this and go over here and look, and here is my equation. It says y equals 71.863x. If I were putting that in terms of Hubble's law, it would say V equals h naught times d. Well, V is y, h naught is the 71.863, and x is the d. The r squared value, that's the goodness of fit, is 0.9566, and that is close to 1, and 1 would be a perfect fit. So 0.9566 is a really good fit to this data. All right, now to finish up this lab, there are some things that we need to enter here. We need to enter our h naught value. We need to enter the age of the universe value. We need to enter our r squared value, so let's call that r squared. We also need to enter in our question 10a.1, question 10a.2, and question 10a.3 values. So I'm putting those notes there, and I'm going to write those values over here to the right of that. So the h naught value I just read off up here. It is 71.863. And the units are kilometers per second per megaparsec, meaning that for every megaparsec of distance, the speed of a galaxy that's receding away increases by 71.863 kilometers per second for every megaparsec. Now, the age calculation is the inverse of this. And go back to the template, look, there is an age calculation formula that you need to do. And when you calculate the age, it's equal to 1 divided by, open parenthesis, h naught times 1.022 times 10 to the negative 12. And don't forget to close your parentheses. So this is an approximate age of the universe based upon the value of Hubble's constant that we found here. Now that's a very big number. It looks like it's 13.6 billion years. So what we can do is divide it by a billion to make it a little more reasonable. So let's go up here to the formula line and divide by 1 billion. That's 1 E9. So that is the age of the universe in billions of years. So let's put the unit over here, billion years. Okay, the r squared value, we also read that off. That's 0.9566. It has no units associated with it. So we need to input our Q1, 2, and 3 values in here now. So we'll go back to our first sheet. Let's copy those. First select it, then Control C, then come back here, and I want to paste them into those squares there, Control V, and there. Now this is the file that you need to save and now submit into the questions. But you also need to post your findings in the discussion. Now go back to the template, look and see what needs to be posted, but they are essentially these values here along with your name. All right, so be sure you post your findings to the discussion, because next week people are going to use your findings and we're going to average everything together and determine what is the best estimate based upon all of our research, what is the best estimate for Hubble constant and the age of the universe. All right, that's it for the Hubble Lemaitre Law Lab. So hopefully you learned something, and have a great week.